Alrighty, so as ever, we're going to be continuing with Desmos on, we're going to be continuing with Desmos with this. This is the 3.6 Desmos practice worksheet, so you can tell it's an original production of mine. This is what you're going to be looking at. Hopefully you have it on Canvas, and so you can follow along with the questions that are going to be at the bottom of the page. But this is going to be the data set that we start with. Cup of coffee is left to cool in a room that stays at 70 degrees Fahrenheit. That is a detail that is meant to throw you off. Don't worry about it. But its temperature does drop over time. So we have time in minutes and temperature of Fahrenheit so we can see how it changes over time. Let's go ahead and let Desmos do some of the heavy lifting here. So we'll switch over, and I went ahead and put in the points for pretty much every table we're going to work at. And I also put in the views. So these are all the different oops. So these are the different values that we have. So at time is 0, we have 180. Time is 1, time is at 2, we have 160, and we have intervals of 2, so we're in good shape here. What is the exponential equation modeling the temperature over time? So question 1, we have a linear one. That ain't bad, but I want the exponential one. So there we go. We have 174.55, and it looks like we've got just a little over a 4% decay rate. Looking at the numbers here at the equation, 174 times 0.958 raised to the x power. So, all right, that's pretty good. What is the coefficient of determination? How reliable is the model? The coefficient of determination, again, I'm not sure if you can see it as clearly on the video, but when you type it into Desmos and you follow along, the coefficient of determination is 0.9896, which is pretty solid by the standards that we have here. So we're in pretty good shape here. What does the model predict the temperature will be after 20 minutes? So again, oops, I forgot to change a couple things around here. So let's see, time and minutes, oops. And you can see I still have the stuff up from the previous one. So there we go. So temperature is our vertical axis, and then time in minutes is our horizontal one. So what does the model predict the temperature will be after 20 minutes? Again, type in expression, and I'm just going to say x equals 20 because that's 20 minutes. I'm just going to slide this over here, and it says that the temperature will be about 74.7 degrees. All right, that makes sense. Yeah, it makes sense. It tracks. So what does the model predict the temperature will be after 60 minutes? All right, well, let's see that. We have x equals 60. Oops, so we'll, now, x equals 60. But about 13 degrees Fahrenheit. So this is where we kind of, this is where it kind of loses the, this is kind of where it loses the, and it kind of illustrates the limitations of certain exponential models, and because exponential models assume a certain decay, a certain constant decay, um, and so there's no way that it's going to drop below freezing by sitting. That hot coffee is going to drop below freezing at the room, and again, this is just one of those. It's just one of those little artifacts that show you some of the limitations of data sets and data modeling. Because apparently, according to this, if you wait an hour, starting with a 180-degree cup of coffee, if you wait an hour, it will be frozen no matter where you leave it. So, yeah, that's pretty funny. I think it's funny. It's pretty amusing here. All right, so we're moving on to problem number 2, which is going to be radioactive decay. I'm going to turn these plots on, and then what I'm going to do is I'm going to change the settings here for the labels. Again, if you go to the right-hand side of the screen, there's going to be a little graph settings button. It'll be above the zoom buttons, but it's a little wrench. And what I'm going to do is for the x-axis, it's going to be time, days. And do you need to do this every single time? No, but it really does help. Oops, mass. But it really does help with if you're asked questions and you need to do, if you're basically going to be asked more detailed questions than what's this number, then it definitely helps having those axes on there. Oh, having the right ranges will too. So x-axis goes from time in days, it goes up to 10 days. So I'll start in -1, and it goes up to, and I'll say 12. All right. And again, it goes up to 12, but it's, oh, wait a minute. I don't need to go up to 12. I can go up to 7. There we go. Goes up to 7. I can get away with 6. I can get away with 6. There we go. And then for the y-axis, we start out at 100, and then we go down to 17. So I'm going to say the y-axis is -10. Give me a little bit of room on the bottom there. And then the top of the axis is going to be, I'll say, about 120. So there we go. Again, like I said, this is more of an art than a science because I had to get all of the data onto the screen at the same time. And you work with it long enough, you can sort of figure it out. But like I said, more of an art than a science. So what is the exponential equation modeling the decay? Well, there's only one way to find out, and that is to hit add regression. Not linear regression. We're not barbarians. Exponential regression. Alrighty. So we start out with 100, which makes sense, and then we have, it looks like about an 18% decay over time. And then r squared gives us a 0.999. So as a excuse me, as a data analyst, this screams that the data is overfit and therefore the linear regression is useless. However, I'm not teaching data analytics, and so for what we're teaching here, this means that the linear regression pretty much follows the data everywhere it goes, and we can count on it to tell us anything that we want to know that the data itself doesn't tell us. So what does the model predict the mass will be after 10 days? Alrighty. Let's see. So expression, let's say x equals 10. Let's scroll this over here. So what will it be after 10? Looks like it'll be 13.62 or 63 grams. So yeah, that's that. There's that answer. And what does it predict the value will be after 25 years? Oh, wait a minute. It's not time in days. It's time. Wait a minute. That's right. Okay, I was looking at the wrong. Wrong sheet. What does the model predict the mass will be after 30 days? Okay, that makes a little bit more sense. After 30 days, all right, we're definitely going to zoom out here. Probably close to 0, if not 0. Yeah, 0.25 grams, yeah. And at a certain point, Desmos will simply say that it's 0 because their their physical spatial limitations on calculators in terms of how much data they can store. So at a certain point, they absolutely will just start rounding down and saying 0. But the fact that 30 days it's still saying that we've got something, yeah, that's pretty good. So yeah, so that answers the fourth question. Um, Next question has to do with investments and growth over years. So that makes sense, but it's also entirely possible when I wrote this worksheet a couple weeks ago that I said, yeah, I'm going to make him calculate years based on an equation that was days. It was like, yeah, that sounds like me. That's why I had to look twice. But anyway, no, that's not the case. So that's as quickly as we're solving these problems. We're basically, most of the time being spent is putting in the data, and then the rest of it is just looking at it and then writing it down and then moving on. So let's move on to the next problem, which is investment growth. So I'm going to go back up to my settings, and time, it's going to be years. So time, years. Then a label is going to be value in dollars. Okay. Now let's see. For years, I'm going to say -1, because again, it's more of an art than a science. And I'm going to say 11. Again, because I'm just trying to fit the information here. And then y-axis. All right, this is oh, okay, that explains why I don't see anything. For the y-axis, I'm going to put 450. And then For the top of it, I'm going to say 900. There we go. So now we can kind of see the data pretty well. Just looking at and again, looking at the table data, um, more of an art than a science, but you can sort of see if I'm going to be going from year 0 to year 9, as far as the data is concerned, having 1 or 2 years on either side of it basically means that it's easier to see. All right, so we're going to go back over, and I'm not going to do a linear. Actually, if you take a look, the linear regression ain't bad. Linear regression is about 0.997 or 0.9985 if you're going to go for a linear one. Linear regression ain't bad. Let's see what the exponential one is. Oh, the exponential one's point is better. It's better by like 0.004. So I mean, exponential one's pretty good too. Uh, with the equation, we've got 502.56, which is stupid because our initial value is 500, but that's okay, Desmos. You do what you need to. And then, all right, so that gives us our equation, 502.57 times 1.057 to the x power. So we've got about a 5.7% growth rate. So that's pretty good. What is the exponential model? So that's what I just said. What is the coefficient of determination? How reliable is the model? R squared is about 0.9998. So by the standards we're doing here, it's like one 10,000th away from being the best you could hope for. What does the model predict the value will be after 10 years? So we'll do the same thing that we've been doing so far. Find an expression. X is time in years, so all I have to do is put in the whole number. So X equals 10, and take a look at what the value is going to be. So it looks like it's going to be $872. All right, well that's not too bad. Let's see what the final question is. What will the value be after 25 years? Okay, all right, here we go. So 25. This one's, I don't need to really zoom out. I just need to scroll over. So time all the way there it is, and time equals 25. Almost $2,000. So okay, that's pretty good. So again, if you want to start out with $500 and then sit around and do nothing for 25 or 30 years, you can get a pretty decent payday. If you're 12. But if you're an adult, you probably want to get a little bit more of a return from your investment. But this is how people build retirements. This is how people build wealth over time. So I suppose it's nothing to sneeze at, but I was trying to force a sneeze there, but it didn't work. Anyway, that's that problem. That's all 4 of the questions for that problem answered. That's how they're all going to be basically solved. But we've got one more. We've got one more table that we got to look at. Population growth in a habitat. Population of insects grows rapidly in a controlled habitat. Let's go to our thing. Let's go to our axes here. So I'm going to label days, and I'm going to start with -1, and I'm going to go through, looks like 10, so I'm going to say 12 again. And then y-axis, population is 50, so I'm going to start at 0. And then for the final one, 560, I'm going to say about 700. There we go. So that allows us to see the upward trend of the data points, and it puts it in the middle of the screen. Like I said, you get enough practice at this, you can be pretty good at it. Now I'm going to add our exponential regression, because I got an exponential one. Linear one ain't bad either, but it's not linear, so we're going to take a look at the exponential regression. All right, yeah, this one is about as good as you can get. So R squared is 0.9999, which, again, for a real data analyst is screaming overfitting of the data, so it's not actually very useful. But that's just me. So what is the exponential equation modeling the population? It's 49.59 times 1.31 to the x. So I mean we basically have a 31% growth rate in reference. So 31% growth rate per day. That is pretty good. I mean that is a lot. Let's see, what is the coefficient of determination? Like I said, the R squared is 0.9999, so it's pretty accurate. What does the model predict the population will be on day 10? Again, I'm going to go up here to add item, expression, x equals 10. So at x equals 10, it says it's going to be about 735. So yeah, that tracks with a 30% daily growth. Now, what does the model predict the date will be on day 20? Oof. All right, 20. You know what? I'm just gonna. Wow. Okay. We're almost there. We're continuing the journey. So at day 20, about nearly 11,000. So wow, we start out with 50 on day 0, and with who would have thought, with just a 30% growth rate and 20 days, 30% growth rate and 20% and 30% growth rate per day at 20 days, that you would get, yeah. So it's a pretty huge number. Anyway, that kind of shows you the sorts of problems that you can solve and the sorts of issues that you can resolve with Desmos. And again, the biggest value of Desmos is you don't have to worry about entering a huge volume of data. You don't have to worry about entering tables of data. In terms of the pen and paper stuff, if you only have 1 point or 2 points, that's the best way to do stuff like this. But if you want to do 1 point or 2 points, that's the best way to do this. But if you want to enter in a bunch of data over time, then yeah, that's the best way to go for it. So yeah, that's going to be it for this worksheet. Next one is going to be, we're going back to pen and paper. So keep Desmos in your back pocket, because we may use it for a later project. But for right now, yeah, we're in pretty good. We're in pretty good shape at how Desmos works and can make our lives a lot easier.